Okay, I have chosen to determine the unknown organic compound called K that we received. First off, I'm going to describe the physical properties. First off, we see that it's a solid white, almost kind of powder, which has no smell at all. And then we'll get into the experiments. The first experiment is the miscibility with water. Uh, in the test, we added the water to a test tube, and then we took a small spatula of our unknown compound and added it to the test tube which had the water in it. Then we used a magnetic stirrer to mix it, and what we saw was that it dissolved completely in water, which means that our compound is polar, and then afterwards we measured the pH to be around 1. Then for the reaction with dibromine, we took around 4 drops of our unknown compound and placed it in a mini test tube, and afterwards we added 5 drops of an aqueous solution of dibromine and looked for a reaction. We then saw that there were no reaction, which means that it is not an alkene because there is no double bonds. Well, meaning that there is no double bonds between 2 carbon atoms. Then for the reaction with dichromate, for this reaction we placed 8 drops of ethanol in one test tube. Then we added about 3 drops of 0.1 molar dichromate. Then in another test tube we added 10 drops of our unknown compound, and then we added another 3 drops of 0.1 molar dichromate. And then we compared the two results. And by looking at it, we saw that there is no reaction, which leads us to the conclusion that it's either a tertiary alcohol or it's not an alcohol at all. Then for the reaction with 2.4 DNPH, we took 10 drops of propanone and added it to a test tube. Then we took 8 drops of the 2.4 DNPH in a 2 molar HCl solution and added in as well. Then in another test tube, again, we placed 10 drops of our unknown compound, and then we added 8 drops of 2.4 DNPH in a 2 molar HCl solution. And then we compared the sites. What we saw was that there were no yellow or orange precipitate formed, and therefore meaning there is no reaction taking place. And by that we can conclude that it's not a ketone or an aldehyde as well. And since we did not get a reaction for the 2.4 DNPH, there is no reason to test with the feline subtolerance reaction. And then to the elemental analysis. For the elemental analysis, we received a paper on our compound which said that in our compound there is 40.68% carbon, and for the hydrogen there is 5.12%, for the oxygen there is 54.19%. And then by converting this to the mass, per 100 grams there is 40.68 grams of carbon. For the hydrogen there is 5.12 grams, and for the oxygen there is 54.19 grams, of course. Then we looked up the molar mass for these for the carbon, hydrogen, and oxygen on the periodic table, and we saw for the carbon there's 12 grams per mole, for the hydrogen is 1 gram per mole, and for the oxygen is 16 grams per mole. Then we calculate the amount of substance by using this formula, where its amount of substance is equal to the mass divided by the molar. And for the result for the carbon, we got 3.39 molar moles, and for the hydrogen we got 5.12 moles, and for the oxygen we got 3.38 moles. Comparing these to each other, we see that carbon and oxygen is about the same, so they will be equal to 1. And then comparing these two to the hydrogen, we see that's almost a half added onto that, so it's a 1.5 for that. And then for calculating the double bond equivalence, we used the handed out formula, and and since we can't use CH 1.50, we had to times it by 2. So we got the formula C2H3O2, and then we could calculate double bond equivalence. And after the calculation, we saw that there will be one double bond per C2H3O2. Then for the next thing we did, we had to figure out the melting point. And by doing that, we used the melting point apparatus. We took our compound when it was in solid state and put it in the melting point apparatus. Then we turned it on and we kept track of it, and we saw it reached about 119 to 205 degrees Celsius. Okay, so now for figuring out what our unknown organic compound is, we had to use the melting point that we just got, and we had to use the elemental analysis to figure out our compound. So we looked up melting points and compared them to each other, and since we knew that our compound had the melting point of 190 to 205 degrees, we looked up C4H6O4 because we had to times the CH 1.50 by as many as it takes to get around the same melting point. So we ended up at the C4H6O4, which is also called 1.4 butanedioric acid. And we did that because it has a melting point of 184 degrees, which means it almost matches up perfectly with our organic compound. Then if we had to use the same by times it up with 4, which means that since C4H6O4 is twice as big as the C2H3O2, it means that there will be 2 double bonds in our compound. And then this is what it would look like for the chemical structure of 1.4 butanedioric acid. And as we see, there is 2 double bonds on the compound. Then now that I have the compound, then I can write out the balanced reaction with water. And we see with the 2 reactants, our butanedioric acid C4H6O4 plus the other reactant water, it formed the product C4H5O4 minus. So we see that it's kind of donated an H, and then it has also formed H3O plus. Then the next thing we did was to compare our compound with another compound with the same molecular mass. And we did this so we could compare the boiling points, and then I can explain why they have different boiling points when they have the same molecular mass. And by doing this, I'm going to use the intermolecular forces. And I'm going to start up the... we had to look up the boiling point for 1.4 butanedioric acid, and it has a boiling point of, as we see here, 235 degrees Celsius. And we compared it to 4-methylpentanoic acid, which has a boiling point of 200 degrees Celsius. So, explaining this difference, we first off going to look at the London forces, which is the weakest force of them all. So it's kind of the most irrelevant. But we see that it's connected to the chain. So the longer the chain, the stronger London force it will be. But since they have almost the same chain, it doesn't really affect the difference a lot. And then we get to the permanent dipole-dipole forces, which is the second strongest force. And in this case, we observed that the 1.4 butanedioric acid has 2 permanent dipole-dipole forces, because it has two double bonded oxygen molecules to a carbon atom. And whereas the 4-methyl pentanoic acid only has one. This is of course then a big reason to why it's bigger. Well, while the 1.4 butane dioic acid has a higher boiling point. And at last, there is the strongest bond, which is the hydrogen bonding, which we see here, which is created between the hydrogens bonding to an oxygen, of course. So when hydrogen bonds to an oxygen, that's the strongest kind of intermolecular force. And we see here that the 1.4 butane dioic acid has two hydrogen bondings because we see the OH is bonded on each side of the chain. So that is very strong. And then compared to the 4-methyl pentanoic acid, which only has one right around here. So because of all these factors that I just stated, the 1.4 butane dioic acid is much harder to break apart because the attraction between all the molecules here is much higher. So that's why it all contributes to the 1.4 butane dioic acid having a much higher boiling point. And yeah, that's it. Thank you.